All right, so this is an introduction to Keylime, which is a new project in the Cloud Native Computing Foundation as a sandbox project. My name is Micheal Peters. I'm an engineer at Red Hat in the office of the CTO, working on emerging technologies, particularly focused on security and emerging tech and security. So to understand what Keylime does, you need to understand the problem it's trying to solve. And that trust is difficult, especially as compute moves out from the data center. So the edge, IoT, cloud, there's some hostile environments that we can be running our compute nodes in. And we don't always have control over the hardware that's underneath. So how do we trust what's running? How do we trust the software that we've deployed has remained the same? How do we know that our nodes haven't been tampered with? And so Keylime comes in to solve this problem. We're using existing technologies such as a hardware TPM and the Linux integrity measurement architecture, which I'm sure most people here are familiar with the TPM. But if you're not, it's essentially a hardware chip that lets you make some cryptographic attestation capabilities, including extending hashes and things like that, similar to a Merkle tree that Luke was talking about, but at a hardware level, such that you can, if you start at the very beginning at the boot of the machine, you can establish this hardware root of trust and then extend everything up from that in various layers. So combining that with the Linux integrity measurement architecture, Keylime can do remote attestation of thousands of nodes. So looking at the scope of what Keylime does, we talked about the remote attestation, which includes measure boot and the runtime checks. We also have encrypted payloads, so the ability to release sensitive data to the nodes after it has passed our verification. So this could include SSH keys. It could include passwords to the cluster, the compute cluster is joining, access to Vault to get other passwords, things like that. And then it also includes a revocation framework. So what happens when something fails attestation? And you have complete control over that, but there's like recommendations on how that can work. But you can do things like cut off VPN connections to isolate it on the network, remove things in an SSH authorized key files and other nodes, but it essentially lets other nodes in the trust boundaries know that this node should no longer be trusted. And all of this tied with the hardware root of trust that we built into the extended up from the TPM. So a brief look at the architecture. Keylime has an agent that runs on the node, which could be the container, the VM, the bare metal machine that we're monitoring, and goes over an untrusted network to talk to the server side, which includes the verifier, Keylime verifier, and the registrar. And these are operated in a secure location, in a secure network, where you have control over that, but we don't make any guarantees or assumptions about the network in between these two. The Keylime agent talks to the TPM to get that data about the different quotes going on and can be polled by the verifier. And this polling can be very quick, on the order of several times a second, where you can poll the agent and find out the state of the machine. So as part of the encrypted payloads that we release when the machine passes at the attestation, the payload can only be decrypted by that node after it has passed attestation, and can also include some auto-run capabilities. So in addition to secrets files that you might release, you could also include a script that can make use of those secrets or do other runtime functions. So the revocation framework is one of the interesting features about Keylime, one of the most interesting. It has a built-in CA plugin system, so you can use something like Cloudflare SSL or something like that. So when a node fails attestation, not only can it revoke the node's certificate, which would break and ring fence that node off from communication from other things, but you can also include, it sends a signed event that to all the nodes in the system that this node had failed attestation, and then you can run local actions. So those can be anything from, like I said, removing an entry in an authorized key file, doing a Kubernetes coordinate drain if you want to isolate the node and move the work off that node onto other nodes, shutting down VPN connections. You can also do other tasks like notify your sysadmins and security engineers via email, PagerDuty, etc. So the way that Keylime works to do the runtime monitoring is by using the IMA Linux subsystem, which is integrity measurement architecture. And this it's not new in Linux, but it's underused. So a lot of people aren't fully deploying it, but it's becoming more and more popular. But essentially, IMA lets you measure every file that's accessed. And you can configure it in lots of different ways, but one common way is that every executable or every library that's imported from an executable or brought into an executable is checked. And so that it's measured, and that measurement is put into a data structure that's then read by the Keylime agent. And this data structure is extended into the TPM. So it can't be altered or compromised without also breaking the entries that are in the TPM. And so the verifier can send this list and the TPM extensions quotes back to the Keylime server side, the verifier, and it can be remotely verified that every file that has been accessed is exactly the way you want it to be. And if it deviates, then the node is revoked. So currently, the work that we're doing to improve Keylime, the Keylime agent is being ported from Python to Rust. This gives us a lot of flexibility for more places to run, including in IoT scenarios and edge scenarios where they can't pull in a lot of dependencies. Situations like a Red Hat Core OS, which is doesn't have a lot of dependencies, like a lot of Python libraries in its base image. Where you couldn't install things through pip and other things like this, but also with a more security-minded language like Rust. So it should give us faster runtime, be smaller, deliverable, and also less dependencies. And that work is ongoing and is making pretty good progress. We're trying to increase the scalability and HA work for Keylime, being run behind load balancers on the server side, connected to shared databases. Just as typical work that you do for scalability. So this is constantly a battle that we're improving, but we're a single verifier registrar pair can handle several thousand nodes, and that can be shared with the database with other verifiers and registrars. And so improving that HA story is something that we're also looking to do. On the future side for making it more cloud native, so the Keylime server side works as containerized images. We want to be able to make like official images builds as part of our CI/CD process that people can pull. And the agent can also work in a container, but it is a little tricky because it needs access to the TPM and to IMA. So depending on what your use case is, some of that works now and some of it doesn't. For instance, if you're wanting to run the agent inside of the container and monitor the container itself, that doesn't work because Linux doesn't have support for IMA namespaces. But that's something that's in discussion and being worked on as well. We also want to make it easier to run Keylime on the server side by having operators and daemon sets for the agents. Although the daemon set for the agent is a little tricky because it just depends on your trust scenario and how you want to work that. Because a lot of times you want Keylime to be up and running before Kubernetes is, so it can't really run under Kubernetes. Because, for instance, if you have it running on all of your compute nodes and you don't want to release Kubernetes workloads to those compute nodes until it's past attestation, you need Keylime running outside of Kubernetes even before that. But we also want to have more built-in or default local actions and revocation scenarios that people can have for common things that they do. For instance, have built-in scenarios for or playbooks that you can run for Kubernetes or various scenarios. So it's a fast-growing project, fairly new, 40+ unique contributors and growing. A lot of visits to our repository. It's a fairly diverse community: IBM, Red Hat, Intel, Netflix, some academic participation as well. As I mentioned, it's a CNCF sandbox project that we're hoping to move up. We have community meetings bi-weekly on Slack, so we're under the CNCF Slack, and we have support for first-time contributors joining in. So thank you, and I'll stop my presentation.